Part 2, Analyzing Rational Functions. Graphs of rational functions can have a variety of shapes and different features. Vertical asymptotes are one such feature that separates rational functions from many other types. A vertical asymptote of a graph of a rational function corresponds to a non-permissible value in the equation of the function, but not all non-permissible values result in a vertical asymptote. Sometimes non-permissible values instead results in a point of discontinuity in a graph. Okay, so we're going to do an example where we have one of these points of discontinuity. Okay, again, not a new concept. You did talk about this in Math 20-1, but, well, we need to review it here. So you see this function, f of x, so x squared minus 5x plus 6 over x minus 3. The first thing we're going to do with any kind of rational function like this is we're going to factor the top, factor the bottom if you can, and just see if anything cancels or that kind of stuff. So when we factor the top here, okay, we see right away, okay, minus 3 and minus 2. Oh boy, the x minus 3's, they're going to cancel. Wow, that's crazy. Okay, so if they cancel out, the function f of x really just simplifies to x minus 2. Now, keep in mind, the bottom still can't equal 0. Okay, because when x is 3, we have a non-permissible value at x equals 3. Okay, because when x is 3, 3 minus 3 is 0. So even if x is 3, even 0 divided by 0, you're still not allowed to do that. So this one still comes into play. It's just the graph doesn't have an asymptote anymore. It's got a hole or a discontinuity. So we're going to graph this. So x minus 2. Okay, x minus 2 has a intercept there and then a slope of 1. Okay, so it just goes like this through there. Now, remember, we still have a non-permissible value at x equals 3. So at x equals 3, 1, 2, 3, we put an open circle here. That looks more like a closed circle, pardon me. Okay, so we put an open circle there, and that's to represent the point of discontinuity. Okay, and we're supposed to identify the point of discontinuity for B. So how that works, for B, what we do is we put that non-permissible value into the simplified equation, because of course it works in that one. So 3 minus 2 is 1. So if x is 3, the y value there would be 1. So this actually works out to the POD, the pod, or the point of discontinuity. Continuity. Okay, and again, I guess I jumped the gun on drawing the graph. Okay, if we know the point of discontinuity, 3, 1, we can actually put the hole around it first and then draw the graph. That way it's a little bit tidier. Okay, but either way you get this graph with that nice little hole in it. Okay, that hole again is called a point of discontinuity. Perfect. Okay, number 2. Okay, rational functions, points of discontinuities versus asymptotes. Okay, so compare the behavior of these functions near any non-permissible values. Okay, so remember we talked about this. Whenever you have functions, we're going to factor the top, factor the bottom, and see what happens. Okay, non-permissible values, notice that they both have the same denominator. So NPVs, okay, that's when 4 minus 2x equals 0. So 4 equals 2x divided by 2 divided by 2, and x equals 2. So there is going to be something going on at x equals 2. Okay, some kind of a non-permissible. So it might be a hole, it might be an asymptote. We have to wait and see. So we're going to do f of x first. So we factor the top. Okay, there's a common factor of x. So then we go x minus 2. Okay, on the bottom, there's also a common factor of 2. 4, whoops. Okay, common factor of 2, sorry. Okay, and then of course that works out to 2 minus x. Okay, So remember the rules on these things. When we factor stuff out, if the factors or the letters are exactly the same, but the signs are different, then we can cancel out, leaving a -1. So this is x minus 2, this is 2 minus x. The x is positive here, negative there. The 2 is negative up here, positive there. So these are those backwards ones. So these really do cancel out, leaving behind a -1. So this is negative x over 2. That's the simplified version for f of x. Now we look at g of x. Okay, so again, we factor the top. So that is x plus 2. Okay, over, we factor the 2 away, and we get 2 minus x. Okay, now this one, we have a positive x and a negative x. Oh, but look, a plus 2 and a plus 2. In order to do that cancellation trick, it only works when the signs are exactly opposite, so these ones aren't that. So this is as simple as it gets. So here, in f of x, the first one, in f of x, the factor canceled, so we're going to have a point of discontinuity. So we're going to have a pod at x equals 2. Okay, and again, to figure out the y-coordinate of that, we just substitute the x value in the simplified expression. So -2 divided by 2, so that'd be y equals -1. So y equals -2 over 2, which equals -1. So our point of discontinuity is at 2, -1. Okay, for g of x, nothing canceled off, so x equals 2, that's going to be a vertical asymptote. Okay, at x equals 2. Okay, perfect. So that's how you can tell whether you have an asymptote or a point of discontinuity. Points of discontinuity cancel, vertical asymptotes don't. Okay, explain any differences. Well, we kind of did already. Okay, f of x has a POD at x equals 2. G of x has an asymptote. I guess we should say a vertical asymptote. Whoops. Helps if I actually hit the eraser button. Okay. Vertical asymptote. Asymptote at x equals 2. Okay, perfect. So that's that one. Okay, we're closing in on it. Okay, number 3. So match the graph. Match the equation of each rational function with the most appropriate graph. Give reasons for each of your choices. Okay, wow, not a big deal. All right, so again, the first thing we do when we see these things is we try and factor. Factor, factor, factor. Always factoring. Okay, so the top here, there's a common factor of x, so then x plus 2. Okay, the bottom of this one, that's a difference of squares. So that's x plus 2, x minus 2. Okay, and oh look, the x plus 2's cancel. So this graph is x over x minus 2. Okay, and we are going to have a point of discontinuity at positive 2. Okay, a vertical asymptote at positive 2 and a point of discontinuity at -2, pardon me. Okay, so oh look, -2, there's a point of discontinuity, vertical asymptote at positive 2, so A is graph 2. Okay, if we look at the B equation, again we factor, so 2x plus 2 there. Now x squared plus 1, okay, that doesn't factor. It's not going to cancel off, of course, with the x plus 2 on the top. The other thing about x squared plus 1, x squared, regardless of what it is always positive. So even 0 squared is positive, -1 squared is 1. Okay, the point is, you're having a positive number plus another positive number. Okay, so the bottom here will never be 0. which means there will not be a point of discontinuity, which means there will not be an asymptote at all for this guy. So we look at the two remaining graphs. Oh, look, graph 3 doesn't have a point of discontinuity, doesn't have an asymptote, so this guy is graph 3. Okay, well, of course, that just leaves graph 1 for this guy, so we could just do the process of elimination, but what fun is that, right? Okay, so we're going to prove why C is actually graph 1. So the top doesn't factor, okay, and then we get x plus 2, x minus 2. Okay, so that looks good. So really, nothing cancels off, so we end up with 2 vertical asymptotes, one at positive 2, one at negative 2. And look, there it is, negative 2, positive 2, vertical asymptotes for both. Okay, it makes this funny squiggle, and we talked a lot about that in Math 20. It's not as important in Math 30. You could just graph it on your calculator to get those, how that graph looks if you really needed to. But regardless, the point here is to be able to recognize that there's 2 vertical asymptotes. So again, graph number 1. Okay, so key ideas for this. The graph of a rational function has either vertical asymptotes or points of discontinuity corresponding to each of its non-permissible values. Okay, it has no vertical asymptote. Okay, so it could either have those or it could have no vertical asymptotes or points of discontinuity. It really just depends on what's going on with the bottom. To find any x-intercepts, points of discontinuity, or vertical asymptotes, we analyze the numerator and denominator. A factor of only the numerator corresponds to an x-intercept. We talked about this a while ago. Okay, these are these zeros. The zeros of a function come just from the numerator. Okay, a factor of only the denominator corresponds to a vertical asymptote. Okay, and then a factor of both the top and the bottom correspond to a point of discontinuity. That's when the top and bottom factors cancel off. Okay, so we get a POD. Okay, to analyze the behavior of a function near the non-permissibles, we can use a table of values, even though the function is undefined or does not exist at the non-permissible value itself. Perfect. Okay, so I want you guys to do some practice questions. This is section 9.2 in your book, starting on page 451. Please do these questions. Again, you can certainly do more if you want or need more practice. Answers are in the back of your textbook, and I encourage you once again to print out the workspace PDF of this, because then you can write all over it. Thanks, guys. See you next lesson.